Our first speaker this afternoon is Representative Engineer Foster and Halvorson. We'll talk about the project in Moscow.
Good afternoon. Again, Bob Halvorson with Halvorson Partners, structural engineers here in Chicago. And I'm here to talk about our concept of Moscow City Tower, which is a 612 meter tall, up to 1,000 foot tall tower in Moscow City. It's a mixed-use building incorporating office, hotel, and condominium spaces. The office space is located in the bottom half of the tower, hotel next, and condominium at the top. The team of people working on the project, the developer is called the ST Group, Moscow-based developer. The architect is Foster and Partners of Chicago. We're doing the structural engineering in association with Waterman International, a London-based firm. We've had an office in Moscow for 15 years. Moscow is an historical city. Many fantastic older buildings. Very few high-rises. These 7 sisters all were built during the communist era for various government agencies, universities, and they represented the extent of high-rise construction in Moscow until the current crop color buildings. Moscow City is about 5.5 kilometers west of the Kremlin, west of the center of Moscow. It's very reminiscent of the Canary Wharf development. You know it. It's even bounded by the river. Previous development had been there. It's cleared away. Master plan, individual plots were sold off to developers. This was I believe, an early rendering of the scheme. You can see that some high-rise building. This was the site about 8 or 9 months ago. Since that time, buildings have sprouted up on the site. I see Turner Construction has a picture of their Federation Tower lobby, and that's, I think, 90 stories. That's most of the activity. The site that I'm going to be talking about is in the back of the current picture. It's this triangular site. It's probably about 800 feet on the size. It's a very large site. The developer of this program called for these 3 components: office, hotel, and residential. And in his mind, there were 3 buildings on this site, in part because he has 3 particular investors who each wanted to own 1 building. So the first initial sketches on the left by Lord Foster was starting to think about the idea of 3 buildings on the site, and since they probably would be built together, looking at some kind of interconnectivity between the schemes. And at the time, on the right, we did some sketches conceptually showing how these buildings could be connected together. And this number 3, we spent some time talking about numbers, and this number 3 became very important, particularly in structural engineering. The site has 3 sides. The program had 3 components. Structurally, to stabilize the point in space, there were 3 forces required. The crescents have triangular 3-sided elements. And simplistically, things like motorcycles on top, which are supported by 2 elements, tend to fall down. Things that have 3 elements are stable, just. And things that are supported by 4 points are, in some ways, excessive, redundant support. And we also spend a lot of time thinking about megastructures. If there are 3 buildings, can we achieve some benefit by tying these buildings together? So just as an exercise in massing, this was the first thing that was built. And after studying it a bit, the architects came to the conclusion that that in fact this large site was pretty tight by the time we put 3 buildings on it. A large portion of the perimeter of these buildings would be looking at the other 2 buildings on the site, and this wasn't a particularly desirable arrangement. So so from this initial study, the massing tended towards this type of arrangement where the buildings became thin blades and they were organized radially, so that there were clear views out and put on the site. And then as we actually took a look at the proportion of these buildings, the height and the thickness, they really exceeded reasonable limits for slenderness in buildings. So again, we started to think about tying these together, as you'll see in these 2 buildings in the back right. And in a relatively short time, 2 or 3 months, the massing evolved to something like this, where there were 3 wings. The wings were tapered towards the top of the building. And the program areas for the office space in the bottom of the building were larger than for either the hotel or residential spaces above, so the taper is natural. Structurally, it does good things, and the sail area is reduced at the top of the building. And that general form was studied in a number of sketches. And again, in short order, it wound up more or less as you see it today. In essence, the building has 3 wings, so each of these wings is 21 meters wide, extending out perhaps 60 meters from a central area. And we started to think about what sort of structural possibilities a plan form and geometry like that could have. And it was, in terms of plan organization, it's really fairly simple. We envisioned some kind of a stiff spine located in the center of the building, and then these tapered wings coming out from that spine would need to be rigid to help brace the spine against lateral loads. And we looked at all sorts of options, from core with outriggers, out of steel and composite. I might add, these are the original sketches. These aren't tactile napkin sketches made up after the fact, so that's why they're a bit rough, perhaps. But there were 2 schemes that particularly appealed to us in that the geometry of the structure related naturally to the tapered geometry of the tower. This one could be called the diagrid scheme, where the columns are sloped parallel to the slope of the end of the wings, and columns counter to that were added. So there were essentially no vertical columns, and these slope columns would carry both gravity load as well as lateral load that were in these columns. And we built a model of it, a model, and it behaved very well. I think there were some drawbacks in the number of elements on the facade of the building. The other idea that related to the geometry was this one. And in this, we came up with the idea of having sloped columns all running parallel to the tapered edge of the wing. And the thinking was that while the columns were sloped, the bays were all typical dimensions, so it was very repetitive in construction from floor to floor. And simplistically, the slope columns would tend to brace the center core. Well, being architects, this is the sketch that came back. And they had the idea of trying to, instead of parallel columns, make a fan-shaped arrangement. Another subtlety of the sketch is that the central core actually doesn't go down to the ground plane. So we thought that was a very elegant form for the structure and create a model of it. And it behaved very well for lateral stiffness and lateral strength, you might imagine. But in terms of torsion, it was relatively weak and not stiff. On the right is a picture of the torsional node shape. So we had to come up, we studied different ways of trying to stiffen the torsion, and decided that the only way that we could really do that effectively was to create diagonals counter to the fan columns. And it wasn't obvious how we could make an attractive pattern given the very low angles of the fan columns. But one day we came up with the idea of, if you will, running the fan columns up to the central core and sort of bouncing what came to be known as reverse fan columns off the core at the same angle. So we developed I think a organic looking tracing pattern that everyone liked better than the previous idea. So this shows the two variants of that. I might add, about this time we studied the idea of terminating the core up in the air like that to create a large open atrium space at the base of the building. But that came attached to about a 9-figure price tag. So rapidly dropped. And this was the first study model showing the gray office, yellow hotel, and red condominium space within the building. And so at the end of 4 or 5 months, we arrived at essentially the final scheme. And the developer was happy with it, the design team was happy with it, and the developer decided to announce it. And this operation announcement took on military proportions in the sense that 4-meter-high models were made and had to be designed to fit through a private airplane door, started off to Moscow, reviewed with Moscow mayor and press, and turned around and went to Cannes and announced it at Nipple. And we were all feeling pretty good at this point that we had a nice tower, a neat building. And then the next day, a call came in, or an email. Somebody said, no, I've seen that building. Oh, no, what don't we know about? Well, it turns out, those of you who have studied the 100 tallest building list put out by the council, there's a 90-ish story building in Pyongyang, North Korea. And it turns out this is it. Now, I don't know how someone got this picture, but the building was apparently constructed, never occupied. There were sort of rumors of structural problems, and we're sort of hoping it's not related to the form of the building. So you've seen, we've talked about the geometry of the scheme, what's it made of. Picture on the left, all the dark elements you see, the fan columns, the reverse fan columns, the bolt elements, the core, are reinforced concrete. The floor framing and bits of other bracing filling in between are structural steel, so it's composite. In essence, all the gravity load, all the wind load on the building is resisted by the concrete elements, which tends to be cost effective in very on steel. The diagram on the right is our idea of how the building will be built. At the top of the sketch there, you see simple lines representing steel erection columns and steel floor framing, so it's directly a steel building. The squiggly lines below that represent the metal deck and the concrete slab. Then finally, the double line structure below that is concrete casing around the steel column. The fan columns do have both a vertical load, a gravity load on them, as well as a horizontal thrust, and that's resisted by large concrete abutments that pass down through the basement levels. This is the architectural office floor plan. You can see the core elements, lifts, stairs. Near the center of the plan, there are escape stairs located in each wing. And this is the corresponding structural diagram. We have the reinforced concrete fan columns with standing columns around the perimeter of the building. Here in the office space, we desired to have open lease space with as few restrictions as possible. So we developed a scheme using composite steel trusses spanning the entire 21-meter width of the building. Mechanical services are integrated within those trusses. This is the hotel layout. The wings were shorter at that point in the building. And then finally, a condominium floor plan at the top of the building. Here, there were less mechanical services running around the floor, and the owner was very interested in maximizing the ceiling. So rather than clear spanning these floors, there were pairs of interior columns, reducing the spans to 7 or 8 meters, so that the floor beams would be very, very shallow. We did not, however, want to carry these steel interior columns down a long distance in the building, basically because of differential shortening concerns between the interior and the exterior. Steel interior columns would be elastic and shorten a certain amount below. Concrete columns, however, tend to creep and shrink over time, therefore shorten differently. And to avoid that problem, at every plant floor, 12 to 16 stories, we actually transferred interior columns out, which has the side benefit of carrying the load on relatively less expensive concrete instead of steel. Well, how does this system fit into the sort of grand scheme of structural concepts? This was a summary of some research I did in 1984 and then repeated 2 years ago in 2004. And it's a plot of buildings that I was able to find. On the left side here are the number of stories in a particular building, and across the bottom are different kinds of structural systems. The lower buildings are frame-type buildings, shear wall buildings, at that point getting up to 50-ish stories. Sorry, the light gray dots are the 1984 data, and the colored dots are the more recent data. And the tallest buildings at that time were 2 buildings abundant, 2 buildings, Hancock and Stewart, for instance. 20 years later, I redid this, and there was sort of a whole new category of building that really didn't exist in 84. There were a few examples, but not enough to be significant. And the scheme that we've developed for Moscow Tower relates in many ways to that scheme, which was a core and outrigger. In essence, a core and outrigger. There's a central spine in the building. There are large beams that go out to grab exterior columns. And the core tends to lean perimeter columns to stabilize the core. Diagrammatically, that's similar to the sketch on the left here. And just to show the similarities and differences, we created these 2 very simple parametric studies of, on the left, a core and outrigger scheme, and on the right, what we're calling a braced spine scheme. For the core and outrigger scheme, the shears, which are plotted here, are only resisted by the core. So those lateral wind shears accumulate in the core and get larger and larger for the base of the building. In this braced spine scheme, essentially the braces act like a support. At each point they touch the core. So the core only needs to span vertically in between those points where it's braced, so the shear forces are significantly less. And similarly, these 2 plots are the moments. And as the shears in the core and outrigger scheme get large, the moments get large. Again, with the braced spine scheme on the right, the core merely has to span between those points of support. So there's some very significant efficiencies in terms of how much stiffness we provide in the core, and there are efficiencies in that all the lateral loads on the building, wind loads, are resisted as axial loads of these slope columns, which is a very efficient way to resist these loads. Now, it comes to no surprise, this really resembles one of those sort of masts that you see out driving around, transmission towers, with a very slender, not very strong, not very stiff center spine that's braced laterally by the cable stays. in our building, those stays, instead of acting compression, or tension, also acting compression. The gravity loads on the slope columns require a horizontal force for stability. So in effect, the gravity load that comes on these slope columns acts as a big three-dimensional arch across, up the fan column, across the floor, and back down another fan column, as indicated on the left side. And on the right is actually a plot of the axial forces of the span columns. And you can see the pattern of the fan column. And so as the span columns come up, the loads tend to arch across the span beams, back down the other side. So this makes the floor framing essential to the stability of the building, which is we are also concerned about the flexibility of the floor diaphragms. The floor openings are very large in the central area, so we have to flexibility of the diaphragm as well. This is a new high-rise building code in Moscow, and I'll just say that once it's translated in English, it's about as equally unclear as but it is clear about a few things. One is progressive collapse, and the code specifically requires that we take out columns and show that the building is stable. So with this intersecting grid of diagonals, when we take out a particular column, as hinted at in this diagram right here, the loads have many ways that they can be distributed. There's a lot of redundancy. So the load could travel, for instance, up this column to that point, and transfer as a compression to here, or it could run up further to other points. So there are many alternate load paths. And then looking at that, we find that the structure can meet that criteria with essentially no additional cost or effort. Buckling design is also a big issue. These are the kind of charts that engineers would look at if designing a normal vertical rectangular building, figure out a K-factor for the design column. Here we have two-story bracing floor, four-story bracing, tips of the wings, and then the fan columns know that 5-story, 10 stories, 20 stories. So the buckling, we actually have to go back to basics and create a very large, nonlinear model of nonlinear geometry, nonlinear material properties, flexible floor diaphragms. So that was a lot of work. We're doing a wind tunnel study, which, like conventional wind studies, looks at the first three modes of vibration, which are the primary contributors. But here we have masts, 3 masts at the top of the tower that extend 100 meters above the observation level. And at higher modes of vibration, the masts can move independent or contrary to the building. So we're having to consider those higher modes. And if you notice on the floor plan, the columns actually are proud of the perimeter wall of the building, so they are exposed to temperature differences. So we've had to do a thermal analysis, heat flow analysis through the columns, and look at the effects of temperature. And then one final sort of fun part of the project is down at the base of the building. The architect is creating a large central atrium by putting in a sloped glass surface in each of the 3 voids between the legs. And we developed, a neat scheme for that. We're essentially creating a truss, a grid network, by creating structural elements in lines that are parallel to the fan column in both directions. There's also a requirement at the base of the screen for a 12 or 13 meter canopy. So we basically took that same sort of structural grid, folded it at that point, and cantilevered out one module of the truss to serve the canopy.
Bob, we have a couple of minutes.
So that horizontal cantilever actually looks like a stiffened element of a plate, if you will. And the net effect is we're able to have entry on all three sides, about 80 meters, column 3. So that's, anyway, a very short introduction to the project. Thank you for your time.